Hello, Calculus 2 students. This is our last video up to Easter break. So we are now at 10.3. This will be the end of what we do from chapter 10, and then we'll go back to some applications of integration. I told you there are 3 principles to Calc 2. Integration sucks. We did that. Integration is useful. We haven't done that yet. But then there's an alternative method, which is Taylor series. Once we're done with that, we'll go back and show that, hey, this all has a purpose. Integration has applications to other fields. So we'll end the semester on that. This last lesson here should take us up through Easter break. So we want to talk about some different ways that we can use Taylor series, and one way is that I don't want to do that chart method every time I have a new series and I want to make its Taylor series. If you look at the 5 listed here, that second one, taking derivatives, I would have to do the product rule, the chain rule, it'd be a mess. Even after 2 of them, I would get sick of it. But we can use series that we know to make these. So let me zoom in a little bit here. The first one is e to the negative x squared. And I'm going to just base that off of e to the x. So e to the x, the series was 1 plus x squared over 2 factorial, x cubed over 3 factorial. And then generally it was x to the n over n factorial. So what I'm going to do here is I'm just going to take everywhere I see x, and I'm going to put negative x squared instead. So 1 minus x squared plus minus x squared quantity squared minus x squared quantity cubed, and in general negative x squared to the n over n factorial. Now to simplify that a little bit, we do want to notice that it's alternating. When you square negative, it goes away, so you get x to the 4 minus x to the 6, and in general it's alternating, but you get a double power of x over n factorial. By the way, this series is one of the ones I told you at the beginning of the semester that cannot be integrated, in the sense that there's no elementary antiderivative for it. But we want to know the answer because that's the standard normal curve, right, for statistics. So you can pretty easily integrate the power series. So that's one big advantage of this. Well, I should say the Taylor series. Now, if I have the same series but I want to multiply it by x squared, you literally just multiply it by x squared. So let's keep going. I take every term and I multiply them by x squared. So all the powers go up by 2, x to the 6 over 2 factorial, x to the 8th, 3 factorial. Still alternating. The powers go up by 2, so I add 2 to the power, and that's it. So that works out pretty nicely. That's a very convoluted series if I want to use the chart, all these chain rules and power rules, but it only takes us a couple steps if we start with a series that we know. Let's get a fresh piece of paper here. The next 2 are related. We're going to make a series and then we're going to integrate it. By the way, that integral, I have no idea how to do that by hand. There might be a trick to it. It's not trig sub though, because it's x to the 4th, not x squared. I have no idea how to integrate that without power series or Taylor series. So let's do this one first. And remember, I asked you last time to memorize 4 series: sine, cosine, e to the x, and 1 over 1 minus x. The closest one is 1 over 1 minus x. So that one was 1 plus x squared plus x cubed. It was just x to the n. So we need to be subtracting something. If we subtract negative x to the 4th, that's the same thing as what we have, right? 1 over 1 plus x to the 4th. So everywhere I see x, I don't put x to the 4th, I put negative x to the 4th. And then I'm going to take it squared, I'm going to take it cubed. And in general, I'm going to take it to the n. So this is alternating. And it's basically power every 4th power of n, x to the 12. And then in general, it's going to be minus 1 to the n, x to the 4n. And if I want to go to number 4 and I want to integrate that, well, I don't know what I should write other than the integral, but on the other side, I can just do the power rule. So x minus x to the 5th over 5, x to the 9 over 9, x to the 13 over 13. The n, it doesn't change. It's an integral with respect to x. So the alternation stays the same. but the power goes up by 1, and I divide by the new power, because that's how you integrate polynomials. Quick and easy once you have series to base them on. All right, this last fifth one is a little bit weird. It looks like 1 over 1 minus x, but not in the way you think. Yes, it's the product of that, it's the square of that, and we'll talk about that in a minute, but in general, multiplying Taylor series, because they're both infinitely long, that's like a nightmare that you would have about foiling, right? What if you had to foil an infinite polynomial? Let's not do that. This is actually the derivative. Let's check that. If you take the derivative of 1 over 1 minus x, think of it as 1 minus x to the minus 1, do the power rule, and then do the chain rule, you get the series that or the function that we're looking at. So that means if I start with 1 over 1 minus x, like we did a minute ago, I take the derivative, so I'm going to take the derivative of both sides. I get the function that I want, and on this side, I just take a derivative. So 1 goes to 0, x goes to 1, 2x, 3x squared, and x to the n minus 1, because that's how you do a derivative with the derivative power rule. So that's all you have to do there. Of course, you have to recognize that that is the derivative in the first place. Now, I did say that multiplying out infinite polynomials is a thing of nightmares. We're going to do something similar anyway. We're going to do some composition, and we're only going to find the cubic, because after a little bit of this, we're going to give up. So trying to find a series like this in general is awful, but remember, a lot of these applications, you just need enough terms to match reality, and oftentimes in reality we round or estimate, and we don't get all the way to the perfect answer. So I want to start, well, it's e to something, so I'll start with e to the x. And I only need a cubic, so we'll just do the first terms up to the cubic term. And there's stuff after that, but we'll stop. Okay, I want e to the sine x. So everywhere I see an x, I'm going to put a sine x. Makes sense. Sine cubed x. Pretty crazy. And then, let me go ahead and just focus on this piece of paper. Well, I don't want sine of x, I want a Taylor series, not a series of sines. Remember that sine x starts out x minus x cubed over 3 factorial. And after that, I don't care because I want a cubic, but I'm going to replace all of these with this. So, and you're going to freak out for a minute, but I'm going to be lazy and skip a lot of what's about to happen because I'm allowed to. Okay, so I get that what you're looking at is insane, right? This is kind of a nightmare. Remember, I only want cubic terms or lower, right? I don't need x to the 4th, 5th, 6th, 7th, any of that. Okay, so the first, this stuff is all good, the stuff I just underlined. I'll copy that stuff down again. What I don't want is, so you look at the next term, if you think about, I get an x squared, but then when you think about the middle term, I get 2 times and then x cubed, x less than x to the 4th term, or the last term times itself, I get an x to the 6th term. None of that matters. So all I care about is the first times the first for FOIL, so I care about x squared over 2 factorial, and then plus stuff I don't want. Okay, and I'm just going to get rid of all that. So I don't mean x to the 1, I mean cross all that stuff out. And then you look at the last one, the only term, if you have 3 of these multiplied out, so let's actually write that out so you can see what I'm talking about. You have 3 of these. The only time I get x cubed or lower is x times x times x. Any other combination is going to have an x cubed in it and then more x's, and it's going to be a bigger degree than a cubic. So I don't care about that stuff. All I care about is x cubed over 3 factorial and then plus a bunch of stuff that I don't care about. So I'm not even going to expand on that because I don't want to live that nightmare. So you look at what's left, and actually the x cubed terms cancel, and you get 1 plus x squared over 2 factorial. That's actually crazy because that's just the beginning of e to the x. That's where we started, except we eliminated the x cubed term. That's not too surprising because sine of x is basically y equals x to start, right? So at the beginning it looks like the identity function. So it's not too surprising that it starts similar. But if you keep going, and I'll show you graphically later, you don't want that x cubed term. It'll start to deviate from what you want at that point. But this would be the final answer here at the bottom. Okay, we have one more on here that we could do two different ways. So sine squared x is the last one we want to talk about. Let me just bring up a blank sheet here. So we're going to do sine squared x. And this one is a multiplication problem. So I can write sine of x times sine of x. And again, we're just doing the cubic. So it's really not too bad. It would be, here's the cubic for sine, and write it twice, and then multiply this out. The factorial goes on the bottom. And if you multiply this out, you can see when you FOIL this, the only thing that matters for a cubic polynomial are the first two terms. Anything else will have an x cubed, and then it'll be too big. So it's x squared plus some junk I don't want. Now, if I wanted to do a quartic or more, or quadratic, or a quintic or something big, this would get more and more complicated. If I wanted the general series for this, just a side note, don't forget all the tools in your toolbox. If I wanted the general series, so a cubic would just be this, or it's also the quadratic. Don't forget, you could also rewrite this. When you did trig sub, you learned that this was also the same as this. And that, if you can do sine of x, you can do sine of 2x, and then you can do these. Right? So this is another way that you could get the whole series for sine squared of x, because it's not too hard to do substitution with this series. So I'll let you think about that, and you can play with that if you want, but the problem just asks for the cubic, and that's this. Just x squared by itself. Okay, so if we go to page 45, this is the end of it here for chapter 10, there's some applications, and again, in math we mean applications to other parts of math. So it says, use series to evaluate this limit. If you know L'Hopital's rule, that's another way to do this limit, but Taylor series work quite well for this. Let's go ahead and do that. So sine of x is x minus x cubed over 3, and there's more stuff. I'll see if I need it later, so I'm not going to write all that out yet. I may not need it. So if I change all the x's to x squareds, if you square the cubic, you get x to the 6th. I'll write that on the next line. Now if I divide this by x squared, I get x squared minus x to the 6th over 3 factorial and some stuff, all over x squared. If I simplify that, I get 1 minus x to the 4th. And then I get a bunch of stuff with x's. Remember that x is going to 0. The limit as x goes to 0 of this. All this is going to go away, and you're going to get a limit of 1. So when you divide by x squared, you divide each term by x squared. Most of them have an x in it, so they disappear. But that constant of 1 up front stays, so the limit's going to be 1. So one way to evaluate limits is a lot of times if you turn everything to a Taylor series, you can see how the degrees might cancel, and then you can get a constant. Okay, so the next problem says, use a Taylor quadratic to solve the equation, and for very small values of x. How close is your answer? So they very specifically say use a quadratic, because this problem is kind of designed to work, let me say. So e to the x would be 1 plus x squared over 2 factorial, but I'll just write 2. And I don't want the rest because I want a quadratic. I'm going to replace e to the x with this. This is x cubed plus 1/8. And I'm going to solve this problem. So I'm going to distribute the 2x, and I get 2x plus 2x squared plus x cubed. The 2 cancels. Plus 1/8. And those go away. Now I've got a quadratic that I can solve. I don't like fractions, so I'm going to multiply everything by 8. So I get 16x plus 16x squared equals 1. If I put it all on one side, I would love to factor, but this does not factor. So we're going to use our good friend, the quadratic formula. Negative b plus or minus b squared. It's b squared minus 4ac. So minus, and then here's 4, and here's a, and here's c. So that's plus 64, actually, all over 2a. Okay, so this number ends up being, let's see, 32, and then the square root. 256 plus 64 is 320. And this is a crazy number, but the thing you should note is that the series approximation is for small values of x, right? We only use a quadratic, so we only want to do things near 0, because that's where we approximated from. So if I do negative 16 minus root 320, I'm going to get a very big negative number. Yeah, I divide by 32, but that won't be as close as if I take negative 16 plus square root of 320, because those kind of go against each other. So the x value that makes these two things equal will be this guy. And I'll show you again graphically here in a minute why this, why you don't want the other answer. So we want plus. And root 320, I can pull at least a 16 out, right? So 16 times 20. 32. So this is negative 16 plus 4 square root 20. Of course, 20 has another 4 in it, right? You could, of course, use your calculator. I'm just being a little bit boring here. So if I divide everything by 8, I get negative 2, 4, plus root 5, whatever that number is. Negative 2 plus root 5 over 4. So that should be a small number that works. And we'll look at that here in a minute. I realize this problem got a little bit boring down here, and I apologize. That one's graphically more interesting. We'll graph it here in a minute in a separate video. Okay, number 3 says find a series solution for this. I enjoy this one. So what we're going to do is we're going to take e to the t, and we're just going to write out some terms. 1 plus t squared over 2 factorial, t cubed over 3 factorial, t to the n over n factorial. We're going to multiply it by t to the 10 to make a series for the integrand. So t to the 10 plus t to the 11 plus t to the 12 over 2 factorial, t to the 13 over 3 factorial, and then t to the n plus 10 over n factorial. If I want to integrate that, well, I just increase the powers by 1 yet again and divide by the new power. So t to the 12 over 12, t to the 13 over 13, but still keep the 2 factorial, t to the 14 over 14, still keep the 3 factorial, and in general, t to the n plus 11, divide by n plus 11, but don't lose the n factorial. So that is kind of intense, but it's quick. And then the question says, what method would you normally use? Well, if I assigned this in Chapter 7, you could have done it. You would have had to do integration by parts 10 times. So this is a much better method than doing integration by parts over and over and over and over. And so we get a series solution that works well enough. Okay, this one is about recognizing that formula. So remember I said in a previous video that it's absolutely imperative that you understand that if you want to model f with a Taylor series, the an right here, so it's an x to the n if you're centered at 0, this is always the nth derivative at 0 over n factorial, or whatever the center is. But in general, right here we're doing 0. That is always the coefficient. So in general, a Taylor series always looks like f of 0, and then the first derivative at 0 times x, and then the second derivative at 0, x squared over 2 factorial, and third derivative at 0, x cubed over 3 factorial. so on. That's always the pattern. So for this particular problem, I want the first, second, third, and 10th derivative. So, well, the first derivative has to be the coefficient of x, which is 1. So for this problem, f prime of 0 equals 1. Now, the second derivative, the coefficients of x squared have to match up. So the second derivative, so f prime of 0 is 1. The second derivative over 2 factorial, which is 2, is supposed to equal 1/2, right? Because of there and then down here, these are supposed to match. So f prime of double prime of 0 should be 1. If you take the third derivative over 3 factorial, it should be 1/3 because that's what's above. Now keep in mind, 3 factorial is not 3, it's 6. So the third derivative at 0 should be 6 over 3, which is 2. The fourth derivative, over 4 factorial, up top it's 1/4. So that should be 4 factorial over 4, which is really 3 factorial, which is 6. And you've seen a pattern for this, right? You got, for second derivative, you got 1, which is 1 factorial. For the third derivative, you got 2, which is 2 factorial. For the fourth derivative, you got 6, which is 3 factorial. So for the 10th derivative here, you should actually get 9 factorial, because that's the pattern. That one got a little bit messy on the screen. Sorry about that, guys. Okay, one more here. I want to find the sum. And this is very similar to the one we did on the practice page that had the problems marked with X's. I'm looking for a function that I know. I got to have those series memorized, and I want to see what was plugged in. Notice all the odd factorials on the bottom and the powers. That should make you think of sine of x. So sine of x looks like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then minus x to the 7th over 7 factorial, and so on. So what it looks like they did, it looks like they plugged in 2. So if you have x equals 2, you get this thing here, which is what they did, 2 to the 5th. And so that's sine of 2 then, is the value that series converges to. Okay, we're going to end with the Plicker's question here. It says, which of the following operations on a Taylor series could change its radius of convergence? And so you may not know this right away, but what you've hopefully seen is that when we multiply by x to the n, or differentiate or integrate, anytime you do those, the radius of convergence does not change. The interval might, the endpoints could change. We saw that with in 9.5 when we did logarithm, and we got ln of 2 for the alternating harmonic series. When you substitute, though, we already saw one on the sheet with the x's, that when we did 1 over 1 minus 2x, we substituted in a 2x, the radius of convergence went from minus 1 to 1. Well, the radius went from 1 to 1/2, okay? So substitution is it. Okay, substitution can change the radius. Okay, and differentiation can change the interval, can change the endpoints. Those are the key facts there. All right, we're going to stop there, and then I'll have a separate video with some graphs throughout all this stuff for you guys to look at, where we're going to do some stuff in Desmos.